All right, class, welcome to chapter 6, where we will talk about two very important functions that we hadn't discussed back since chapter 1. We've finished all the library of functions that I introduced to you in 1.3. And so now in this chapter, we're going to talk about exponential and logarithmic functions, which happen to be two very famous inverse functions of each other. So we could have discussed this topic of inverse functions all the way in chapter 1 when we discussed functions, but maybe weren't quite as mature algebraically to hear about them. So many textbooks introduce the idea of inverse functions only at this chapter of, again, exponential and logarithmic functions, because you do absolutely need to think of them as inverse functions in order to introduce them. So first things first, only one-to-one functions have an inverse. So if you do remember from chapter 1, we discussed that a one-to-one function has to pass the horizontal line test alongside, of course, every function has to pass the vertical line test. But only one-to-one functions also have to pass the horizontal line test. So for example, a parabola, such as the one I just drew for you in the corner, does not pass the horizontal line test because there's a horizontal line that crosses it in more than one point. So therefore, that's not a one-to-one function. However, if a function is not one-to-one, such as the parabola, to find its inverse, we still can. However, we have to restrict the domain of it. So it's like, yes, it does have an inverse, but not on the whole all real number domain, just on half of it. Okay, so we'll see how this happens before the end of the section. Now, what is the inverse of a function? First things first, the inverse of a function is labeled by this very unfortunate notation. And I'm saying unfortunate because you know the power of -1 means reciprocals, means to take the reciprocal of a function. So I'll tell you in a minute how we need to be careful about this. So it does seem like it would be the reciprocal, but it's not. Okay, so what does a one-to-one function do? Well, what does an inverse function do? An inverse function is one such that if I take the composition, and if you remember we talked about this in 1.4, composition of two functions. So if I find the composition of these two functions, which by the definition is f of f inverse or f inverse of f, we get x. So what this statement simply says is that once one function is acting on x, and then the other one comes and acts on the result of it, as you see, the x comes back as clean as it was. So in other words, whatever one function did to x, the other one undid it. Okay, so very famous functions, inverse functions of each other, could be the squaring and the square rooting function. So if one is squaring something, and then here comes its inverse function and it square roots that value, what happens, a square and a square root cancel each other out, and then you get x out of it. So that's what inverse functions are. We're going to talk about a bunch more in a minute. So let me discuss first the notation of this inverse functions. Be careful, as I said, with the notation. The reciprocal of a function, therefore, will be labeled by this. If I want to take the reciprocal of a function, I have to put that function in parentheses with a -1 exponent. This is what we have if we want to take the reciprocal of a function. As we know, a -1 exponent means to write it in the denominator, right, of a fraction. The rules of exponents. So again, if that's what I want, I have to put the f of x in a parentheses with a -1 exponent, and that's going to mean the reciprocal of it, 1 over f of x. This -1 is put right next to the function, right? That's a notation, okay? All right. So what would be examples of inverse functions? We've used this, believe it or not, since the very beginning of this course. You've used inverse functions all the time. Adding and subtracting are inverse functions. So inverses are functions that undo each other. Whatever one did, the other one comes and undoes right back. So how are these inverse functions of each other? Well, we can do what we call composition of functions. So if you remember that, we substitute one function at a time. So first thing, I'm coming and I'm replacing f inverse with whatever it equals to. And now f of x minus 4 simply means in the function f, wherever I see x, I have to write x minus 4. And there you have it, x minus 4 plus 4, that's x right back. So whatever one function did, the other one undid. I can show you this also with the little boxes that I drew for you. So let's say I'm plugging the number 3 into the function f of x. That says, well, add 4 to it. Great. By adding 4 to this 3, I'm going to get a 7, right? So if I plug in a 3 into this function, I'm going to get a 7. Now, composition of functions means they're acting one in a row after the other. So you first put a value through the function f of x, then the result of it gets further put in through the machine of this next function. So if I put in 7 through the x minus 4 machine, 7 minus 4 equals to 3. So this is what we're saying, that a function and its inverse undo each other. So once any number goes through both machines in a row, one after the other, they come back just as they started. And again, if you wanted to put 3 through the function f inverse first, so let's say we're plugging it through the x minus 4 machine first. Okay, then 3 minus 4 is a -1. Then when we plug this in through the f of x machine, that adds a 4 to it, to whatever comes its way. -1 plus 4 is back to 3, right? So it doesn't matter the order through which we let them go. So let me show you again what are other famous inverse functions. Of course, multiplying and dividing are inverse operations, therefore inverse function. If one multiplies the 3 and the other one divides by 3, they undo each other. As I mentioned before, the squaring and the square rooting function, it doesn't matter who's who, they are inverses of each other. Okay, cubing and cube rooting. So again, they're inverses of each other. Doesn't matter which one of them I'm starting with, right? So inverse functions are the ones that undo each other. Now, it is really important to see that if, let's say, a point of coordinates x comma y is on the graph of f of x, then yx must be on the graph of the inverse function. So here, if I take these functions up above, first ones that we looked at a little bit more in details. So once we plugged in 3 into the f of x machine, 3 plus 4 was 7. Then we plugged in 7 into the inverse function machine. Then 7 minus 4 was back a 3. So this is what I'm saying. The input of one function is the output of another. This is the output of f of x, and it's the input of its inverse, right? So functions and their inverses swap input versus output. You plug in a 3, you get a 7. You plug in a 7, you get a 3. Okay. So because of this, the following statements are true. A function and its inverse are symmetrical about the y equals to x line. So let me draw this y equals to x line. Y equals to x is this line right here. Goes through 0, 0, 1, 1, 2, 2, and so on and so on. So let me show you the cubing and the cube root functions. And show you how exactly, and just last week we were talking about the cube root function, and I was showing you or telling you how a cube root function is really a cubing function sideways, right? The same thing with the squaring and the square root function, right? The parabolas. Here is the square root function. Now, of course, the squaring function goes all the way, but if you're going to put the squaring function on its side, then again, this is also why only one-to-one functions have an inverse. So maybe I should have sketched this for you. So the squaring function, x squared function, is a full parabola. You see it does not pass the horizontal line test. And so if we put this on the side, if the original function does not pass the horizontal line test, the new function, when it goes sideways, it won't pass the vertical line test, so therefore it's not a function. Okay, so that's why, and we already know that the square root function does not at all look like this red one that I drew for you, but that the square root function is only half of it, yes? So therefore, yes, the squaring function has an inverse, but only restricted to the positive x values only. Remember, the square root is the positive root of a number. It's not the negative root of a number. So if you're going to use the square root symbol, then it only applies to the positive side of the x squared function, right? Not the negative side. So therefore, to find an inverse of a function that's not one-to-one, we restrict the domain. So we cut it to where it does pass the horizontal line test. And then its inverse will pass the vertical line test. And we're going to see an example at the end of this section. And so again, because x's are the domain and y's are the range, and because a function and its inverse basically swap x's and y's, then a function and its inverse will swap domain and ranges. So let's go back to this x squared function, which we already discussed one more time. So where do we restrict its domain? Again, the x squared function has a domain of all real numbers. So we have to restrict its domain to a piece that is one-to-one. So we cut it from the vertex only the right side, okay? And then when you flip this over, you're going to get the square root function. So remember, when we solve an equation, let's say x squared equals to 4 or whatever, and we square root both sides, yes, then we get plus or minus the square root of 4. What does that mean, plus or minus square root of 4? The positive square root of 4 and the negative square root of 4. These are two functions, actually, right? If we just want the positive square root, then we only keep the positive x's. Okay. All right. So let's look here really quick. This is just let's see, theory behind inverse functions. And let's play some more with the numbers and practice on what inverse functions mean. This should be pretty easy. Actually, one of the examples I gave you earlier. So if you plug in 3 into a function and you get 7, what happens if you plug in 7 into the inverse function? You must get a 3. Same thing. Let's say you plug in -1 into some function and you get 8. That means the inverse function evaluated at 8 must equal to -1. So they swap x's and y's. Okay. That's when you deal with inverse functions. That's what they do. So, but I leave it out. Okay. So, here, let me write it out. What is f inverse of -6? That simply means this is the function of f of x. So what I need to look at on this function, f of what is going to equal to 6, so that I can swap it and get this what value up. So what I'm looking at is, when does this function equal to -6? I'm sorry, -6. It equals to the -6. So the function equals to a y of 6, of -6, when x is -4. So therefore, when I swap these around, I'm going to get -4. So f inverse of, so again, what you need to think is which y value of -6, if the y value is -6 on the function, then what is the x value to it? Okay. So same thing, the y value on the original function is -3. What is the x value to it? -2. So we're looking backwards. The y value on the original function is -4. What is the x value to it? -3. So we're just basically reversing with an inverse function the places of x and y. Okay. What if I asked you this funny question? What is f of -2? Just wanted to pick a good one. Like that. So what this actually means is to look at what? The reciprocal of f of -2. Well, f of -2 is -3, and I want the reciprocal of this value. So be careful where your -1 value is, right? If it's right next to the function, then it means inverse functions. If it's in a parentheses on the outside, that's when we mean reciprocals. All right. So last question or last thing is, how do we find the inverse of a function? We kind of already know +5, -5 are going to be inverses, cube rooting and cubing, but we already intuitively know what the inverse function is. I've told you about it, but let's see how we truly find that to be true. So there are a few steps here. It says, first things first, replace f of x with y. That's true. That's what a function stands for, the y values. So that's nothing new. Now, a function and its inverse, swap x's and y's. So let's do that. So as soon as we swapped x and y, this function right here is already our inverse function. So all we have to do at this place is solve for y. Great. So to get y by itself, I have to undo the cube root, just as we did in 5.1. That means cube both sides. So here it is, x to the third is equal to y. This y right here, as I said, is already our inverse function. So we're going to replace it with the inverse function notation. So the inverse of this original function f of x is x cubed. So let's try this again with this very simple looking function. Replace f of x with y. Swap x and y. And then solve for y. So to get y by itself, we have to minus 5. So as you see, the inverse function of your original function is x minus 5, as predicted. Here's another one. This one's going to be tricky, but let's see. Replace f of x with y. Great. Swap x and y. So wherever you see a y, you write an x. And wherever you see an x, you write a y. Good. Now solve for y. So to get y by itself, there's quite a bit of y's around. No problem. The first thing to solve for y is to get rid of this big old fraction. So to get rid of a fraction, as we practiced not long ago, we are going to multiply both sides by the denominator that I want to get rid of, right? So that's how we get rid of or solve fractional equations. We multiply by the LCD. So the left-hand side is a 4xy plus 5x equals to 2y minus 1, right? The denominator went away. Great. So remember, you want to solve for y. And the thing about solving for y is that we want the y's to be on the same side of the equal. So therefore, we do a swapping. I'm going to minus the 2y over to this side. And then also I'm going to minus the 5x to the right. So I have 4xy minus 2y equals to negative 1 minus 5x. The order in which I write those terms does not matter. And so at least just like any linear equation that we have, and this is a linear equation in y, as y is to the power of 1, we want to get the variable terms to one side, which we did. And if you solve a regular equation in one variable, you're not going to see a second variable. And therefore, you could put these terms together. And we can't do that here, but one way to see the y only is to factor it out. So once these y terms are together, we factor out the y. So y is going to equal to negative 1 minus 5x divided by 4x minus 2. That's the inverse function. So this one's tricky. I wouldn't put it on a test for you. I didn't even put in the homework. But I did want to show you. Yeah, what we do. These are the steps. Substitute f of x with y. Swap x's and y's and then try and get y by itself. Now, just like in any other equation where the variable shows up in multiple places, you got to put those somehow together and make that variable come up only once so you can solve for it. All right, and here it is again. This one should be a little more straightforward. Substitute f of x with y. Swap x and y. As I said, this is not going to be as bad because as you see, your y that you need to solve for shows up in one place only. Great. So how do I get y by itself? Well, I'm going to minus the 1 over. So that's how we get rid of adding. Adding and subtracting are inverses of each other. They undo each other. The next thing that undoes each other is cubing and cube rooting. So I'm going to cube root both sides. Okay. Then on my way to get to y, what else do? I have to add the 5 over. And finally, to undo this multiplication by 2, I have to divide by 2. So here with this problem, I did want to show you all the different ways to undo operations. If you have adding, you subtract. If you have subtracting, you add. If you have multiplication, you divide. If you have division, you multiply. Cubing, cube rooting, and so on. So one more thing here, I'm going to replace y with f to the negative 1 of x. There you go. That's my inverse function. All right. So here is one more. We already know quadratic. Find the inverse of the following functions, which there's only one to worry about. Set restrictions on the domain if necessary, and state the domain and the range of the function and its inverse. Okay, so it will be very helpful to graph this quadratic function, and then I'll show you how easy we can restrict it. And we've already practiced on solving I should say graphing quadratic functions. This quadratic went 2 units to the right and 3 units up. Therefore, the vertex is at 2, 3. So 2 to the right, 3 up. Great. Now, it said, do not keep the whole parabola. It's not going to have an inverse, but cut it all the way to the vertex. So we have to take half of this parabola away and only keep half of it. So that's all that I'm going to throw on the inverse side. So therefore, when I find the inverse of this function, because we say we only keep the positive x's and swap the x and the y, and then solve for y. So minus the 3. Take the square root. And now instead of putting plus or minus, we only keep the positive one of them, not the negative. So just the positive square root of x minus 3. And the last thing, of course, is to add 2 over. So here is my inverse function. It's the square root of x minus 3 plus 2. And where's this one going? I'm going to draw it in blue. It's the square root function going 3 units to the right and 2 units up. That's exactly on the other side of the y equals to x. Very nicely, you see how they're inverses of each other. We swap the x's and the y's. The starting point now is at 3, 2, which makes sense. We went 3 units to the right, 2 units up. So let's also write the domain and the range of these restricted. You can even see it from the graph. The domain of the square root function is just 3 to infinity. Its range is when 2 units up, right? You see it from the graph, is just 2 to infinity. Now, on this function right here, even though, of course, the domain of, if you want to call it the restricted f, you want, but it says find the domain and the range of this restricted function. So we cut it only from 2 to the right. Right? We cut half of the function away. We kept only the side of it that was starting at 2. So the domain and range of a function and its inverse should be opposites to each other. So the domain of one is the range of the inverse function, and backwards, as you see. Now, of course, it's easy once you found one to just swap them around, and then you have the domain and the range of the inverse function. So here it is. And that's 6.1.